So now, again, this is a presentation for SER222, also called CST230, at ASU Polytech. We're using the textbook Java Software Structures by Lewis and Chase. You can either be using the 4th or the 3rd edition. And today we're going to be continuing our discussion of stacks, but we're going to talk about another way to implement it using a linked structure, a linked list. It's important that you don't just watch this lecture, but you read the book, because the book talks in more detail about inserting and removing from the middle of these linked lists, and they can be quite complicated. So please don't just watch lectures. Please read the books. Read the book. I can't stress that enough. So the scope of the chapter is going to be about referring to object references as links and organizing your data using a linked structure versus an array-based structure. So, we're used to arrays where the order of items is really based off of where they're located in memory, right? Adjacent items in a collection occupy the references to them occupy adjacent memories locations in an array. And to get to the middle of it, you can just do kind of memory address arithmetic. You just add 10 to your address and you're at the 10th reference, right? Whereas a linked structure, you have to daisy chain through things. It's going to be a lot more complicated. And we're going to look at a linked implementation of a stack, which is actually going to be quite simple, even though in general these linked structures can be quite complicated. So a linked structure is an alternative to array-based implementation. So each object in the collection is going to have a reference to the next object, to the next one. And in order to get through all of the items in the collection, you can just keep following those references from next to next. So it's really like a barrel of monkeys, where you have one monkey, which is grabbing onto the next one, which is grabbing onto the next one. And they're all just kind of hold themselves together. And if you were to just pluck one out of the middle, you'd lose access to everything that followed. So, for example, if you have a person object, each instance could have within it a reference to the next person objects. And then a series of person objects would make up a linked list. So you just, for your list, have a reference to the first person. And then that first person has a reference to the second, who has a reference to the third. And finally, the last person has a reference to null, to nobody. And if I wanted to access the third item in order to get to him, I'd have to say front.next to get me that third item. So you can't just jump into the middle, you have to travel through everybody, like a game of telephone. Now this is a linked list, nice linear structure, a list. But links are going to be used quite a bit to represent arbitrary structures. So it could be this messy. So this is called a DAG. It's just an arbitrary directed graph, right? This could represent rooms in a building or regions in an image, or nodes in a network, right? So it can be arbitrarily disorganized. But for now, we're focusing on a very simple linked list item. So we've got that each object has a reference to the next object. Let's assume that reference is called next. So we're looking right now at some code that would show you how to visit each item in a linked list. So instead of using a for loop, what you have to do is you have to create a reference to the current item and start off with that referring to the first thing. Now if the list is empty, first would be null, and then the following loop would not execute at all. Otherwise, current isn't null, so you can print current. And then you can set current equal to current.next. And so that'll kind of take you through the entire list until eventually current.next is null, and so current becomes null, and then you bail out of that while list. So this is just your generic code to traverse all of the items in a linked list. You have to be careful with these links, because like I said, you've got a chain. If you remove one link in the chain, you remove everything below it. If you're not careful with the order in which you do these operations, you lose access to stuff. So in order to insert a node at the front of the list, So you have to take your list. So you've got a new node, and you've also got your front pointer here, pointing to the beginning of the list. And they're kind of showing you the order in which you have to do things. You have to take a new node and set that new node's next to be the front of the list, and then you have to make the front of the list be the new node. And now if you follow it, you can see that it's a proper list. If you do these in the wrong order, you'll have to figure out what happens, but it'll be bad. Okay. Similarly to deleting a node from the beginning of the list is pretty straightforward. All you have to do is set front, which was here. You set front to reference the same thing that front.next referenced. So this is front.next. So you're going to set front equal to front.next. This deleted node, if nobody's referencing it anymore, the garbage collector is going to delete it, so it won't be a memory leak in Java. So far, our linked list has looked like this because the person class kept a reference to the next person. But in general, you don't like that coupling between the element and the collection that's going to contain it. You don't want to write a class which must only be stored in linked lists. It's better to write a person class, and then we can have a separate node class. And that node class can have two references, one to the next node and another reference to person. And that way the designer of the person class doesn't have to be aware of the fact that it's only going to be stored in a linked list. So we're going to call these things nodes, and each node is going to have a value and a next, or a data and a next field, right? So just like an array, your cells point reference the data. That's the way our linked list is. Only they're going to have one reference to the data and one reference to the next. So each one of these references is 4 bytes. Each node is going to cost us 8 bytes, right? Plus however big the data is. So in linked lists, this linked list here, you can see that each object has a single link to the next object, and that you know that you've hit the end of the list when that link reference to null. So we're going to call this a null terminated singly. Well, we're going to call this a null terminated singly linked list. And this we're going to call a doubly linked list. So it's another variation on it. So in addition to each node having a reference to the next item, the nodes also have a reference to the previous item as well, which means that each node now has not 8 but 14 bytes of data associated with it. So it uses a little bit more memory, but just order n extra memory needs to be used. The beauty here is that you can easily traverse this list not only forward but backwards, whereas the previous one you can only traverse it from front to back. So this could be used to implement a doubly ended queue, for instance. Okay, so that's enough about linked lists. Let's go back into stacks and see how we would implement a stack using a linked list. I hope it's clear. We've seen how to insert and remove from the front. So for a linked list, we can have the top of the stack be the front of the list. Now, if we were to make the top of the stack be the back of the list, we'd have a big problem because it's hard to remove from the back of the list. Right? So, again, Java's stack class is derived from a class called vector, and it's since stack kind of restrict the set of operations, there's no object-oriented mechanism to restrict the set of mechanisms to get rid of something that you inherited. So it's kind of a little bit of a problem how this object hierarchy is organized, but you just have to live with it. There is another interface in the Java API called double-ended queue, DEQ, which also has the push and the pop. But the interesting thing about DEQ is it combines a stack and a queue, which we're going to learn about later. So it still does more than what a stack does. And also a linked list in Java. The Java linked list class it looks like this. It's the doubly ended one. So you can insert and remove from both ends. And it's an implementation of double-ended queue. For now, we'll use a deck as our stack. So even though we're using a double-ended queue, it's really kind of, we're going to think of it as a stack. And now we're going to consider the problem of traversing a maze. So you can suppose that a two-dimensional maze can be represented by a grid of 1 to indicate a path that you can follow, and 0 to indicate a wall, a barricade that you can't pass. And our goal is to start from the upper left corner and finish in the lower right, or the bottom right corner. We can't move diagonally, we can only move left, right, up, and down. And we'll assume that our data starts with the number of rows and the number of columns, so that we know how big the array is. We can probably, or the maze is, we can probably store this in some kind of an array. And then we're going to have to implement an algorithm that's going to do sort of a depth-first search. It's a search strategy to try to find a path that gets you all the way to the end of the maze. So using a stack, we can perform a backtracking algorithm, depth-first search, that finds a solution to the maze. And an object representing a position in the maze is going to get pushed onto the stack each time we try a new path. And if a dead end is encountered, we're going to pop that position, and then we're going to try another path. And if that fails, we pop it, and we're going to keep popping our way back till eventually, hopefully, we find the solution. As we visit each position in the maze, we're going to change it to represent a tried path that failed with a 2, and a tried path that hasn't failed with 3. So the maze represents a maze of characters, and the goal is to get from the top left corner to the bottom right by following the ones. Okay? So here's our class maze, and we're going to use these constants. Tried is 2, and path, meaning so far, as far as we know, it's successful, is a 3. And we're going to have fields to represent what we read from that text file. So we have an integer for the number of rows and the number of columns, and a two-dimensional array, or an array of arrays, to represent the grid. So we're starting with our maze class that actually represents that maze data, and we're going to do some file I/O. And whenever you're accessing a file, it might throw an exception if that file can't be found for whatever reason. This is a runtime error because somebody might unplug the USB stick after calling the functions. Right? So we're going to take a file name. We're going to use a scanner to parse the data. So we make a new scanner for that file, where the number of rows is the first integer, the number of columns is the next integer, and now we know enough to allocate the grid. So we're going to instantiate integers for number of rows times number of columns. And then we're going to do a double for loop, once for each row, once for each column, and we're going to use next int to get the zeros or the ones out. So this kind of reads in that maze data, and we're going to have some methods. So tried position is supposedly a method that was tried but failed. When we say try position, it's just going to mark it with a 2 as something that we tried but failed. Now I've got to just point out really quickly, I'm not entirely sure that the author's code represents these two enumerations properly. We'll have to see whether they ever mark things as a successful path. I'm not sure that they do. So we'll find out as we review this code. But when we try a position, we mark it with a 2, tried. We also have accessor functions to get the number of rows and to get the number of columns. And then a function to mark it as a successful path. So if you say mark path, that'll put the 3 in there. It marks it as a part of the successful path. Okay, so we've got the ability to drop our breadcrumbs. And now we've got to have a method to know whether it's possible to visit a certain cell. And it's going to be possible to visit a certain cell if it's a 0, basically. and if it's within the grid. So if you go past the edges of the grid, you can't visit it. So let's see how this works. So valid position, we're going to say, can I go to row and column? If the row is greater than 0 and less than length, and the column is greater than 0 and less than the length of the first row, they should have called get rows and get columns, shouldn't they? They've already got a get rows and a get columns method. I would have used those here. So then they say if it's a valid position if grid row column is equal to 1. I'm sorry, I think I said 0 before. The 1 is the part of the maze that you can actually visit. So if it's a 1 and it's inside the grid, result is true. Otherwise, it stays false, and that's what you return. So valid position doesn't change anything, it just tells you whether you can go there. And then, of course, we have the ability to print the grid out. So this is using string concatenation. It should probably be using a string buffer, but it goes through each row, goes through each column, and outputs the value there, followed by new lines. So that's our maze class. It's got some abilities to manipulate and explore the maze. Now we have our maze solver, which is going to implement our backtracking algorithm that's interesting. So the maze solver is going to have a reference to the maze that we're trying to solve. So you pass that to the constructor, and it saves that as an instance variable. And now it's going to have, this is kind of the important one, a traverse method. So it's going to use, so it's going to keep track of the current row and column and whether or not we have successfully traversed the maze. It's also got this class called a position, and I think a position is just going to be a tuple. It's going to contain both the row and the column that we've tried. And now we have a stack of positions, and because the double-ended queue has the same interface as a stack, they're using a deck as a stack. And deck is an interface, and the linked list is a class that implements that interface. So this is really our stack. And the first thing that we're going to do is we're going to push our initial position. So we just push that upper left corner, right? So this is 0, 0. That's the default. Right? So while we haven't found the treasure at the end of the maze, and the stack is not empty. So if the stack ever happens to be empty, then that means that there is no path from the beginning to the end. You're completely blocked off, right? So the stack isn't empty. So while there's still places to explore, we're going to pop off the next unexplored location. So as we go, when we see every time we move through this maze, we're going to add all the future places we could explore onto the stack. And stack.pop pulls up the next unexplored location. It might have been explored. The next potentially unexplored location. And then we go to maze try position. So what does try position do? So try position is just going to mark that position as tried. It's going to put a 2 there. Right? So it puts a 2 in this current position. Now we're going to say if the position is equal to the bottom right corner of the maze. So we've gotten all the way to the bottom right corner of the maze, then we're done. We've solved the maze. We've found the treasure. Otherwise, we're going to push onto the stack the element just to our left and just to our right and just above us and just below us. So we're going to potentially explore the 4 adjacent cells to us. Right? So is this correct? Let's take a quick look real quick. Notice that if I'm not mistaken, we never called valid position to check to see if a position was valid. Right? So my question for you guys, I guess, is this code correct? I never saw it mark a solution as part of the path, and I never saw it check to see whether a position was valid. So what I think that this should be doing right here is checking to see checking to see if the position is valid before it does anything else. So either before it pushes it onto the stack, it should check if it's valid, or as soon as it pops it, one or the other. Right? Actually, I'm wrong. Notice that it's calling this method push new position. So it's not calling stack.push, it's calling a method called push new position, and it's using snake. This is the snake style naming convention where you're using underscores between words. And the author is doing something which is really annoying here, because this is not Java's naming convention. Java likes you to use leading lower camel case, where push capital N new capital P position. That threw me for a loop. So this is actually calling a function called push new position, and what that's doing is before it pushes it onto the stack, it creates a new position object, sets the x and y, and before it pushes it onto the stack, it makes sure that it's valid. So there we go. I didn't see this being called before, and now I see it being called. So it never is going to push an item onto the stack for the maze unless it knows that that position is valid, meaning you haven't already explored it and it's not a wall, right? So, and then finally you have the maze tester class, your driver code, and what that's going to do is load the maze in, and it's going to run the solver. And if it successfully traversed it, it's going to print that it was successfully traversed. Okay. So one thing that we should note is this never marked the successful path. Yes, it never actually marked the successful path. It just tells you whether a path existed or not. So that's the maze example, and there is code provided by the author for the maze example, so maybe we can try to trace through how. So I have here the so I have here some Java source code that I pulled from the course website for the maze tester, and I pulled it into the IntelliJ IDE. I downloaded, unzipped it, and I pulled it in. And right off the bat, I'm getting these squiggly lines for linked stack. But if you recall, linked stack wasn't actually used by the maze, and these squiggly lines correspond to these little red bars here that are to be completed as a programming project. So all I'm going to do is, this is the code I downloaded, and I'm just going to go ahead and delete that for the purpose of this presentation, since it's not used anyway. And now it should be safe for me to run the maze tester using the double-ended queue for the maze solver. So it's using a deck here. So I should be able to run that in Java. It's making it, parsing, running. Enter the name of the file containing the maze, and I believe it's in the current folder. I can say test file .text, and so it's printed out the maze, which is just sort of this one little diagonal thing. And now it shows me the maze successfully traversed. You'll notice it didn't print any 3s, it just did 2s. And let me try the same thing again. If I run it, let me go to maze tester just to make sure I understand how this works. If I run it again, and I say test file 4.text, it's a much more complicated maze, and it looks like it didn't quite visit everywhere, but it hit a dead end and went back and went down, and it ended up eventually solving the maze. And if we wanted to print a little bit more, we could modify the maze solver just for this course so that every time through this loop, what we could do is we could print the stack. I'm sorry, this isn't Python. S out. There we go. So I could print out the stack, and then I can print out the maze, and I could print out just a blank line, and or maybe I'll print out something like that. So I'm printing out some debug information at every single step, just to help make sense of this, and we'll see what happens if we run that. Oh my goodness. So if you guys don't know, I'm a Python programmer, and so I will tend to, in whatever language I'm supposed to be using at the time, I'll spontaneously switch to Python. Sorry about that. So let's try this with test file 2.txt. Oh, that's a big one. So I don't like the way that it's printing the stack, because it's just printing the class name. So position is this class that represents a position. It's just got x and y. Get x, get y, set x, set y. The issue here is this does not have a toString, so I'm just going to go ahead and add that so that I can print them out well. So actually, I want to implement a method here. So I think that this tool makes that easier, makes that easy in some way. Again, I'm not entirely. Here we go. Generate. So Alt Insert. I can generate by toString. So this is smart enough to come up with something useful. And I'm not going to print the word position first. I'm going to print a left parenthesis and a right parenthesis. So this is going to be x equals y equals in parentheses. And so now if I save that, I've got a toString method, so instead of when I try to display the stack, it's not going to show me a bunch of position, position, position. It's going to actually show me the stack. So let me run this. I didn't like test file 2. Let me do test file, the first one. It's short. Okay. So let's look at what we got from this. We pushed, the only valid position was 1, 0. It was popped and tried. I'm sorry. Yeah, it was popped and tried. Then we had 1, 1 got pushed. This one right here. Then we have 2, 1, 3, 1. So the stack never really grew very far in that one. Let's try to look at test file 3.txt. I have no idea what's in those ones, so we'll see. So we can kind of get a sense for what's going on by looking at these. So it's kind of a big maze, and from the first position, we just find down. That's the only direction you can go. And from that second position, the only direction that you can go is right. But here we can see once we're here, we're gonna have two different options. So the next one, we could have gone down or right again. So we could put two positions on the stack. We're gonna pop and try one of them. So I'm not quite sure which one of those two we try. Actually, do I know? We're going to do 2, 1. So x is 2, y is 1. So we move to the right, and then we push more. So we kind of see this stack growing with options as we go. So there's our stack, and there's our maze as we're working our way down. So maybe you can study those and get a better sense of how it works. And you saw me override 2 strings. So this is sort of the maze code. It does actually run. It does actually work to traverse the maze. And so now back to slides. Right now we're waiting for... Let me pause the recording. So we can implement our own version of a stack that uses a linked list to hold the elements. We're going to call it, following our naming convention, we're going to use the first word of the way that we implemented, so just linked, and then we're going to use the interface stack. It stores objects of generic type T, and is going to implement the stack ADT interface that we've already done in the previous lecture. It's going to use a separate class called linear node of T to actually form the list, because whatever T is, it doesn't necessarily know that it's going to be in a list. So that linear node is going to hold a reference to an object of type T and also a reference to the next linear node in the list. And in order to keep track of how many things are in the list, we're going to use an integer variable count. So since all activity in a stack happens on one end, we only need to refer to one end. So the front of the list is going to be our top. For some data structures, you might also want to have a pointer to the tail, but in this one, we don't need it. We can just refer to the top. The count is, of course, the number of nodes. Each node references some data and references a next node. So the stack can have A, B, C, D pushed in, and if we see here at the end, the top of the stack is the last one that was pushed was a D. So this is how it looks. Count is 4, and they kind of show up in reverse order, which is what we want from the stack. In order to push E onto the stack, so going from D being at the top here to E being at the top, and D appears to have shifted to the right. All we've done is we've inserted to the front of the linked list. So what we did is we created a new node, we set the node's value to E, we set the next to D, and then we set top equal to this new node. Then we incremented count. We'll see that when we look at the code. So here we actually have it, the code for a linear node. You have a reference to the next linear node, and then a reference to the element stored at this node. It's got a default constructor that sets those both to null, and then just for usability, you have a constructor that constructs it with an element and sets next to null. And you have an access function to get the next item, which is a linear node of T again, and you have a mutator to change the next item, so to set it equal to some other node. You have an accessor to get the element and a mutator to change the element stored at this node, not to change which element is stored there. And then again, the actual stack implements the interface. It has a field for the count, and it keeps a reference to one linear node, the top, and it starts off kind of as null. So in the default constructor, we set count to 0 and top to null. In order to push a new element, we first create a new temporary variable, and we assign it to a new linear node instance where the element is the one that we're trying to push. Now we take that temporary node and we set its next pointer to be the current top of the stack. Then we set the current top of the stack to be that new temporary node. Notice, of course, you don't need the word this dot. It's optional in Java. And we increment our count, our internal count. Okay. So this has now been pushed onto the stack. To remove, we need to make sure that it's possible to remove, and if not, we'll throw that empty collection exception. Otherwise, we need to get the result, which is the top.get element. We need to do that before we get rid of top, or we'll lose access to it. Then we set top equal to top.next. Okay. And we decrement count because we have one less item. Nothing should refer to top anymore. That linear node will end up getting garbage collected, and we return the result. Okay. So, adding a node to the front of the linked list, it's kind of important that you get these two operations in the right order. You have the temp node that's going to be the new front of the list, and you have to set the next thing to be top before you make top equal to temp. If you do those in the wrong order, you end up with some sort of a crazy cycle. Right? So that kind of wraps up our discussion on stacks and implementing stacks using links. This is the fourth consecutive slide I've done today, so I'm going to take a break. And I hope these videos help you, even though they get a little bit long.